now. Okay, so I will present certain achievements in the direction that is stated in the title of this talk that we have done during the last semester. So this is more or less work in progress and tried once. So before we, what should I press to get to the next slide? Yeah, like this. Before I start speaking on more technical stuff, I would like to describe the educational setup that that I was facing. So I'm teaching bachelor in mathematics course within bachelor in cybersecurity or programming, approximately 200 students, and they are pretty much newbies and everything when it comes to the university studying. So it's the first year, it's first semester, it's a small course, and it's unfortunately the only mathematics course during their three-year studies. So they don't have very strong prerequisites in mathematics, and they, unfortunately, most of them don't have prior programming knowledge. The course, well, it's not called Discrete Mathematics, but that's what it essentially is, consists of the following parts. So there is some set theory and elementary logic, some combinatorics, some number theory and related crypto like RSA algorithms. So we have some graph theory and a little bit of linear algebra, but in a very, very limited way. So like solving linear equations and not much more than that. So when it comes to the graph theoretical part of the course, so many students consider it being relevant, and they tend to show a little bit more interest compared to the other parts of the course. And there are quite some relevant applications, like things on network analysis, or the traveling salesman's problem, or some other graph traversing things like find the shortest path, or find the cheapest way to fly from A to B, and so on. So the course has traditionally had some focus on the algorithms like breadth first search, depth first search, some or Dijkstra's and Prim's algorithms, and students like it. Unfortunately, when it comes to the question, why actually do these algorithms do what they are promised to do, then students start having issues, and the proofs are inductive, and induction is something that we sometimes take in the course, but they are still rather new with it. And mathematical induction, if you meet it, if it's your first meeting with it, it's kind of a big story. And when on top comes something that is rather complicated and that you are trying to prove by use of induction, the story gets double as hard. And part of the problem comes from the school mathematics, which in Norway is represented by the lower part of my slides. So you have an equation, and they use the formula, and then essentially the only non-trivial part is to identify, to kind of color the letters, I would say. So where is B and where you should put the B. And then the next non-trivial part is to make the computations, and so then you're done, more or less. And there never comes an explanation for why this formula is actually true. Well, you can compute and put the numbers back, but not something general. And this is something that we want to break, because we think that this is not essentially the mathematics. So if we speak on a little bit higher, with higher level formulations, so we want students to produce something authentical and find some arguments for what they are doing is correct. And this is essentially a proof. So why do we need a proof? Or what actually is proof, and how can you argument that something is correct if you don't have external authority like a lecturer or the book that you can always refer to and say, yeah, it's correct because of that guy told that it's correct. So we actually want students to start experiencing this very special moment when you're becoming unsure. You have done something and you don't know whether it's correct or not. And looking a little bit further in their development as programmers, then we want them to practice in constructing algorithms, which means working systematic and being aware of the system that they are following. And unfortunately, we cannot just say, dear students, please start doing this. We have to find some lower level problems that actually involve all these elements. So, graph enumeration problems. This is a classical subject. There is a famous book of Harry and Palmer on graphical enumeration, which goes very deep in details and shows some ways further in the abstract algebra. But we take it on a lower level, and a typical example could be: could you please produce and show us all trees on 5 vertices? So just find everything that is a tree and that has just 5 vertices. And then the problem naturally divides into 2 collected things. The first one, which is easy, is to just find some trees. The second thing that is difficult, and it is actually opening for the things I shown on the previous slide, find all the trees. And then when I observed how the students work with these types of problems. So at some points, all of them come to me and ask, yeah, but you know, we found whatever, we found 17 of these graphs, but how do we know that there's actually not number 18 in the picture? And for many, at least this is my own personal opinion on the story, this is for many students, that's the first, in a way, the first point when they see something, they have produced the result, and they are in need of the arguments to show that actually this result is something real. So that's one thing. Another thing, that's this is training on solving this kind of problems, gives a training in pure concepts. So you should comprehend what a tree is if you are working on this problem. Which is part of our course curriculum. And this is also a good practice in graph isomorphy, where the students have essentially all the time to answer the question, okay, I have an example and another one. Are they the same graph or not? And this is also part of our curriculum, so something that study program wants the students to go through and be familiar with. Yes, and all these problems, they are essentially a part of what in the deductive studies, well, it was George Kinnair who has shown me this, given example type of problems. So essentially, giving examples and construction techniques, and this we should understand as the ABC formula for quadratic equations, is rarely sufficient for most learners, as though many people still consider this being mathematics. But to get a deeper understanding, they need to construct their own examples. And then we are up to the next challenge, which is a teacher challenge. We have to assess all this somehow. So besides our practical issues with being 200 students and usually very few teacher assistants, and many being online, and it seems that this is going to be the new normal, so many just don't want to come offline irrespective of the measures we are taking. So there are too many students, that's one thing. And another thing, this is a demanding story. So if we compare to the problem to quadratic equations, there it's sort of easy. Many TAs are getting quite skilled on seeing the error. But these are some pictures that I just found on Stack Exchange with some graph theory questions. Yeah, okay. So for example, on the left, the 6 non-isomorphic trees are listed below. So, but why on earth are they non-isomorphic? So if you're a student assistant who just works like 2 hours a week or whatever, 6 hours a week with this course, and you're getting shown something like this and not drawn nicely like it's done here, but rather on paper with some kind of unclear edges and so on, this is a big story. The picture on the right is, I would say, it's even worse. It does have, though, some data that was clearly meant to sort of show us that these are these are non-isomorphic. But this is not something you can do on the fly. This is something that needs deep analysis, that needs that really the student conversation partner sort of press the brake and starts thinking. And this is not something we can do in the practical setup that we are having. So just to finish the didactic stuff, so this is essentially something that we want our students to come to at the end. And here are some problem-solving techniques. For example, a few mentioned by Paulia in another famous book, How to Solve It. So if you want to list all graphs on 6 vertices and you consider it being a hard problem, could you please do it with 5, 4, 3, or maybe 2 vertices, and then look how the problem develops. So this is about identifying a parameter, and here it's quite natural. It's either its number of something, either number of edges, number of nodes, or number of something more interesting. And then we look at how structure develops. So this is a sort of preparation to the inductive proofs that are quite common in graph theory, and this is something that can be also done by quite weak students. So okay, if you cannot do it with 6 trees, maybe with trees on 6 edges, on 6 nodes, sorry, then maybe you can do it with trees on just 2 nodes, and so you see how pattern develops. But this is something like this small conversation. This is something that we keep for this private talks, either during office hours or in the exercise sessions. But the biggest story is done by the computer. So when we are coming to the computer business, we meet the next challenge, and the challenge is that we need to input the graphs. And in computer science, there are 3 representation forms, which is matrix, list, or drawing. And we have tried a few. Actually, we have tried all of them. So the illustration here is actually from an exam that I prepared for 1 year ago, and there we have to use some awkward system called Inspera. So, I mean, there is possible to enter. It's possible to enter matrices, but this has to be done in this kind of in the table form. And I mean, come on, guys, there are 5 nodes, and you have to enter 25 entries, and most of them are zeros. Okay, so I have pre-generated zeros. This is possible, but still, this is quite lots. And if you need to enter several graphs, this gets even worse. And then in the analysis of the matrices, you have to take account of different permutations, and there is some other stuff. So lists, that's another thing, which is sort of okay when people are studying Python programming, and then they have a nice picture on the left, and then they have just to store the nice list of lists on the right. But still, this is getting very long. So if they have to input lists manually, this is a big story. Then we still do have some permutation issues, renumbering of the nodes if we want to assess the graphs. And then this is very much error prone. So what we don't know if we formulate problems in this way and students fail. So do they fail because they don't master the tree concept, or do they fail because they do not master the matrix concept, or the same like a graph theoretical concept, or just this matrix list thingy? And this might be not a big story for like 3rd-year students who've done quite a lot of programming and who see night dreams in Python. But for the 1st year and 1st semester, this is a big story. And all our experience with the student panels is essentially that many complain that difficult input makes them really hate system. Like multivariate analysis with stack, quite many say that we hate stack because it's so hard to enter these large formulas. So the drawing is easy, is natural, and it's a natural representation for those who start doing it. But then we face this challenge of inputting into some computer system. So our solution uses CodeRunner, which is a quite standard plugin for Moodle, mostly meant for programming. So just students write some code, it's run through unit tests, and then if you pass, then you get some score. But then, surprisingly, there is an input type that allows to draw graphs, and there is also a Python package on the nets, which is called NetworkX, that can do whatsoever with the graphs. So we have installed all this on this Job server that runs the Python code. And then we let students draw, and then we get a Python structure from CodeRunner, and then we send it to NetworkX, and then we can just write something like this to assess whether the student's graph was connected or not. And then I see that I do have still a few minutes, so I think this was the last slide here. So I'm going to do a new share. And then I should find my Firefox window, and then that was the conference. And then I made a small quiz with a few questions that we made in our course. So the first question: draw a complement of complete bipartite graph, where first part has 4 and the second one has 3 nodes. So drawing is very easy. I just click like this, and when I shift click, I make an edge, and then it's done. And then I can do check. And so what students see is this CodeRunner test. There's just one test here. So what we have done, this really looks like cheating, I would say. This is a standard function to create a complete bipartite graph. Then we take a complement, which is also a standard function in the NetworkX, and then we just run this check, which says, okay, are these two isomorphic or not? And then done. And then we should get true, but if in this case we obviously are not getting true. And so students have unlimitedly many attempts to get this true. Next example. This is about finding all non-isomorph trees with 6 nodes. So everything is here. So that was one tree, and then I can draw another tree, and then just make it into a tree. And then I try check. So how does the assessment look like? Well, we check whether the graph is simple. There are no loops, and then we create NetworkX structure for the answer. And this is a little bit ugly, but we are doing it graphically. So essentially we draw ourselves all these graphs and then store it and then get this kind of structure. And so we check whether, again, this forest, then it's not a tree, it's a forest, one forest and another forest, whether they two are the same. So this can be clearly done better. So the students essentially see the answers here, because this is just a list representing the graphs or all the edges. We can see it like this, while 42, 45, and so on being the node names. So this can be hidden, and some extra PRT style assessment can be done. So, for example, we can go through all the components, check whether the number is correct, and if it's not, then we can check whether some single graphs are isomorphic with others. So this is kind of a little bit more work, but it's possible to do within the same within this context. Number 3, something like this. What is here? 5 nodes. Then there should be Euler cycle in all graphs. So everything that has an Euler cycle and 5 nodes. So same type of thinking. We just provide an answer and we check whether it's isomorph or not. Here, I guess it's pretty much the same. Just draw some binary tree that has exactly 24 nodes. And what is important with these kind of problems, that there are quite a few, there could be quite a few different answers that we all will accept as correct. Here, I think this was the 5, so 6. Here it's just draw all non-isomorph graphs that are connected and that have four nodes. This doesn't have 4 nodes, but here my colleague who programmed this, he made some dirty trick. He essentially didn't like the idea of showing the graphs in the code, because this code is being shown to the students. So he made a hash table of the real answer and then of the student answer, and so he compared hashes, expecting that then the hashes will fail, will be different if the two sets are different. Still, I think this is kind of all this is trial and error, but still I think the sort of PRT type of thinking with partial points for partially correct. For example, if there are 6, there should be 6 graphs, but student found 5, then this should get some answers. Some student should get some points for this. And then the last, here we actually use CodeRunner as it was supposed to be. So we have decided to actually teach students using Network X and graphs. So there is some code that's kind of tutorial. Do like this and you create a graph, do like this, and then you will have nodes, and do like this, you will have edges. And then they should program, just make some connected graph with four nodes. So this is essentially, I would say, this is a normal programming exercise as people do in this Python programming courses. Just that we have integrated it into our mathematics course, because I mean students have to be programmers anyway, and then they also get some idea how we check what they have done. That was and maybe the last thing. So surprisingly, all this worked, I would say, because these are complex systems, and then you start installing some third-party packages here and there. We didn't get a single complaint about from the students that something didn't work or was unclear, and this I consider a big way forward compared to like entering matrices, where everybody meant that this is a complete disaster. And then, well, there was also one complaint from students who meant that there was too much drawing and too limited mathematics. But I think that guy sort of was in a way too smart with mathematics, because the non-trivial part is not drawing. The non-trivial part is actually finding all these graphs. So we cannot, in this way, we cannot assess their thinking completely, but in this way, at least we can automate quite a lot. And I think there were a few speakers in the morning who said that we actually make the very limited and valuable student assistant time. We use it differently. We use it for consultations and for work on more non-trivial stuff, compared to just looking at different pictures and trying to figure out what's wrong there. So this means that students have done it a few times themselves, and when they really don't understand, then they contact me or assistants. Yes, I think that was pretty much what I wanted to show during this half an hour. Any questions?
Great. Thanks a lot, Andrey. I'll give a clap. Yeah, there's the link to posting questions to the Moodle pages in the chat, but also if anyone wants to unmute and ask a question now, that'd be great. Actually, I have a question. I hadn't seen this Moodle quiz where you're drawing your nodes and edges. Is that something that you can demonstrate, like upload to the EAMS site an example, or is that something that needs extra?
No, so I can do it, no problem. We can upload an example. So this is a standard feature in CodeRunner.
Oh,
so
right,
Moodle,
okay.
Moodle has to have a CodeRunner plugin. So I talked to Richard Loeb, who is the author of Code Runner. So he said that all this drawing was essentially one master project of his programming students. So they didn't think that actually it will be used for other purposes. So what we've been speaking with them now, that this will be just sort of a standard type of input for Code Runner, because we still have to do the conversion of their structures to network X. And then to really use these questions, you have to have different Python packages. For example, NetworkX installed on your job server. So this is the server that runs the student code that has Python and everything on there. So it's not, I mean, it's not that straightforward, but it's rather easy if you have good access to your IT support.
Right. Well, hopefully Christian or someone could sort that out. That would be great. But yeah, I think it's a really interesting idea to teach proofs using graph theory is a great because you can really get into the proofs and things. So that's excellent. Yeah, any questions? Let me refresh there's no questions on the Moodle site.
Okay. Yeah.
Okay. Well, if there's no one else, thanks again very much for your talk. And yeah, it would be great to see an example if you could upload that somehow to there's like a play area, I guess, is on the EAMS site.
Yeah, I would say the one maybe last thing. The good thing is that you can really mix this with Stack and other Moodle types. So this all lives on the same platform and same infrastructure. So it's quite important that it's not being separated into different stuff. But so do a little bit of math, do a little bit of programming, and then combine the two.
Great. Excellent. Okay, thanks a lot. Okay.